Howdy students, this is going to be a continuation of 13.1 and this is going to be our last and final section for this first part of notes. In this video we're going to look at rate law, what it is, and how to write the equation for rate law which governs the speed of a reaction. So a rate law is an equation that's written and it expresses how the reaction rate of a particular reaction is dependent upon the concentration of its reactants. So we're going to be writing an equation that uses molarities as it relates to time, and we're going to learn what a rate constant is as well. For the reaction A plus B yields C plus D, the general form of a rate law would be rate equals the letter K times brackets for A, which is concentration, to the power of A times the concentration of B to the power of lowercase b. Now, A and B are reactants. Little a and little b are coefficients. You'll notice that in a rate law, we are not concerned with how much product is produced. We're just concerned with the speed at which product is produced. So we're going to learn how to write an equation that looks like this. So here's the general form. Rate equals K, A to the power of an exponent, B to the power of an exponent. Rate is usually expressed as moles per liter times time. So concentration times time. The letter K is the specific rate constant. It's a constant for a given reaction at a given temperature. The faster the reaction, the larger the K value. Every K is unique to each reaction that we have. So there are millions of chemical reactions, which means there are millions of K values. A and B represent the concentrations of reactants A and B in moles per liter. X and Y are what we call the orders of reactants, and we're actually going to have to determine these by looking at experimental data. So the last part of this video is actually just going to be going over examples on how to look at experimental data to determine these exponents. These exponents are positive integers, not fractions. So really, we'll have 0, 1, 2, and in this class, we're going to stop at the third order reactions. So these are the possible values for the exponents here, and our goal is to identify those numbers. So how do we do this? Well, we're going to have to use experimental data to determine this. If we double the initial concentration and it causes the initial rate to also double, we call that a first order in that reactant. If it quadruples, we'll have a second order in that reactant. If it increases by 8-fold, the reaction is third order. And if it doubles but nothing changes, then we have a 0 order. So fill these in. We're going to see how these apply to the examples in just a moment. And then I'm also going to summarize at the end of this video. The exponents determine the order of the reactants. The sum of all the exponents is what we call the overall order of the reaction. So if we look at this example up top, rate equals K, A, B squared. There's nothing listed here, and if there's no exponent, it's assumed that there's a 1 there because anything to the 1 exponent is itself. And then we have the squared value here. So if I was looking for the overall order of the reaction, I would add 1 plus 2. And that would give me an overall order of 3. So we would say that the reaction is third order overall. Now this other example down here, A is to the power of 3, B is to the power of 2. So overall, we have a fifth order overall reaction. But if we're looking at each reactant, we can say it's third order in A and second order in B. Okay, last part of this video, we're going to be looking at some experimental data, and we're going to determine the rate law based on the experimental data. So here's my reaction. A yields B. Remember, we don't use products in a rate law. So right away, my general form is rate equals K. And I'm going to open up a bracket for A because that's one of my reactants. And my goal is to find this exponent, but I have to use experimental data. So what I need to look at are the concentrations of A and how that affects the rate. So A, from trial 1 to trial 2, doubles. It goes from 0.05 to 0.10. We want to know what happens to the speed, the rate of the reaction. So 3 times 10 to the negative 4. And then 1.2 times 10 to the negative third would be 0.0012. So here to here, it is going to quadruple, which is a factor of 4. So to determine the order, this is what I teach my students. The concentration doubled by a factor of 2. The rate quadrupled, which is a factor of 4. So to find the order of the reactant, I need to figure out what exponent makes this true. 2 to the what power gives me 4. And if you know about your exponents, 2 to the second power would give me 4. And that is the order of the reactant. It is a second order reactant. And this is your answer. So I'm looking for the rate law equation. This is what we would be giving. Let's look at another example. My reaction is getting more complex up top. I'm not going to look at the products. I have a coefficient here, but I'm not going to use that for the rate law. We want to know, based on experimental data, what the exponent is. Rate equals the rate constant, K. I'm going to open up brackets for A, and I'm going to open up brackets for B. My goal is to find the exponents of both. So now we have 2 reactants, and there's one thing we have to be careful of. If I'm looking at A, I have to look at A where B does not change. In any good experiment, you don't want to change more than one variable. So that's what we're going to do. So let's look at where A changes, but B does not. So B does not change from trial 2 to 3. There is no change here. But for chemical A, we double our concentration by a factor of 2. The rate goes from 0.2 to 0.8. So we quadruple it by a factor of 4. So for chemical A, doubling the concentration quadrupled the rate. The exponent that makes this true is a 2, just like the first example. So it's rate equals Ka squared. And I'm going to have to do the same thing for chemical B. So again, if I'm looking at B, I need somewhere where A doesn't change. So A does not change from trial 1 to trial 2. B doubles. What happens to the rate? It also doubles. So for chemical B, we doubled the concentration. The rate was also doubled. So what exponent makes this true? Well, again, if you know the exponent rules, anything to the first power is itself. So 2 to the first power is 2. So B is a first order reactant. And this is our final answer for the rate equation. And then we have one last example. Here's a reaction. A plus B yields C. The rate equals K. I will not be using product C. I'm going to look at A and B together. So here, if I'm looking at A, I need B to stay the same, and that happens from trial 1 to 2. The concentration of A doubles here. But look what happens to the rate. It does not change. So I'm going to say that that changed by a factor of 1. It didn't decrease, it just stayed the same. So for A, we doubled the concentration, and the rate stayed the same. So 2 to the what power gives you 1. So if we know our exponent rules, anything to the 0 power is 1. So for reactant A, we have a 0 exponent. And that whole term is actually going to cancel out because of that. So we're not even going to have A in our final reactant rate law. For B, we need A to stay the same. That happens from trial 2 to 3. B doubles from 2 to 3. And the rate doubles. So for B, 2 to the what power gives me 2. That would be a 1. So if I rewrite the rate law, it would be rate equals K times B. And you could put the 1 there if you'd like. It's not necessary, but the A is not even going to show up. And I actually believe, yes, we do have one more example here. We're going to look at a real live reaction involving ammonium and nitrite. And when we put those two polyatomic ions together, we get diatomic nitrogen and water. So nothing's changing here except we have real chemicals. So instead of A, B, and C, we're actually going to use real chemicals. And after we find the rate law, we're actually going to solve for the value of K. So I'm going to start out. My rate is going to equal the letter K. I have NH4 plus as one reactant, and the other reactant is NO2 minus nitrite. I will not be using products in rate law. I need nitrite to stay the same. As I look at ammonium, it doubles here. The rate goes from 2.7 times 10 to the negative 7th to 5.4 times 10 to the negative 7th, which is a factor of 2. And so when we have the doubling of ammonium, 2 to the first power will give me 2. So ammonium is a first order reactant, and nitrite, we want ammonium to stay the same. During those two trials, we doubled the concentration, and the rate is also doubled. So for nitrite, 2 to the first power is 2. So this is also a first order reactant. Now, we have our rate law. The last part is actually to solve for the value of K. And to do that, we actually pick a trial, and we're going to plug in all the values. So I'm going to pick trial 1. Here's my rate law, NH4 plus times NO2 minus. And I'm going to plug in the values. So the rate is 1.35 times 10 to the negative 7th equals, I'm solving for the value of K, so I'm going to leave that as my variable. 0.100 is the molarity, the concentration of ammonium, times 0.005 for the concentration of nitrite. When I solve for the letter K, my value is 2.70 times 10 to the negative fourth. And there are no units for the specific rate constant. But this specific rate constant is unique for this particular reaction.